So obviously, today's lecture will be slightly different than some of the others you've had. Today will definitely be a little more conceptual rather than research-based. So again, like I said, I grew up in Bozeman and ended up in this class 7 years ago exactly. So I'm where you guys all are currently. And yeah, it was definitely a transformative experience to have been in this class because I never would have thought that it would have put me so far onto the path towards research, and for that I'm forever grateful. My personal research topic is focused on the protozoan parasite Toxoplasma gondii and its transmission dynamics in both human and wildlife. So if any of that sounds interesting to you, feel free to reach out to me as well. Like specifically, I'm looking at the Monterey Bay Shed water system, as well as looking at risk factors for exposure in Brazil, since congenital toxoplasmosis is a very big issue, especially due to the lack of water sanitation and higher environmental exposure in Brazil. So even though my research doesn't directly work on COVID now, just from being an epidemiologist during this time, I've had a lot of exposure. And I think that it is important just for the general public, especially students like yourselves, to learn more about the modeling process and some of the little logistics between all of the graphs and all the information that's being thrown at you. So it is very overwhelming, and it's hard to take in so much all at once. So just as a recap, even though I'm sure you have all gotten this from other scientists like Raina Plowright and David Quammen, epidemiology is a study of the distribution, determinants, and control of diseases at the population level. And some of the key questions that we're really interested in are who and what gets a disease, how, and where and when are these outbreaks occurring. And obviously, these questions do involve a lot of in-person work and in-person screening, tracking, surveillance. But because of the nature of epidemiology and the goal of bridging both theory and application, there is a strong role for mathematical modeling and statistical modeling. So again, because a lot of this information will be a little bit perhaps higher than like the understanding for some of you. The main takeaways I hope that you guys can get from this lecture are mainly that try to understand the goals of models when you come into contact with them, accepting that all models, no matter how perfect, have limits, and that each time when you choose a model, you are making certain trade-offs. So as we touched on before, in answering those questions of, like who, what, when, why, how, like why are we really using models? And specifically for an epidemic or a pandemic, we want to calculate the expected size. We want to know, the speed of the spread. We want to forecast expected deaths, which is the metric that we've seen in the news most often. We also might want to find out the effects of intervention. So a lot of science and a lot of studies have been done on masking and social distancing. And especially in the early days of the pandemic, we didn't really know which ones were really effective or not. And we can do that with modeling because if we were to have done an actual study with masking or social distancing, that might have taken 3, 4, 5, 6 months. Or with another drug, might have taken like 3, 4, 5, 6 months. But with modeling, you can get those results quicker, even though they might not be the most accurate to what reality is. And again, just hammering the point that that at the end of the day, you really want to bridge theory and application. And I think that's a core component of epidemiology and public health. So like when you know all these metrics, expected deaths, size of epidemic, it's really going to help public health officials, determine how to best allocate resources. If in November there might be a peak, okay, then Public health officials can say like, okay, we need to ramp up social distancing, we need to ramp up masking, we might need to amp up production of masks. And, really like these are things that will help us, beat this pandemic and get ahead of it while we still can. Before we really move on to the nitty gritty, I do, again, just want to highlight the long process it takes to to modeling in the first place. So, a model isn't useful if it doesn't have some degree of truth in it. And truth is, in us, in the public, and in the real world. And so before we even, touch or even think about the model, there are people out there, doing contact tracing, finding secondary contacts, getting those people tested, validating that they actually have COVID, compiling that data, distributing it to other public health officials. People are cleaning that data, compiling it so it's ready for modeling before we finally have a model that's, somewhat tangible and comprehensible. And the thing is, even before we get to the final model, we have these compounding levels of uncertainty and potential error. So, even in the most perfect world, there's no way we're going to capture every single case. There's no tests. There's very few tests that are 100% accurate. There's, again, like potential errors and failures at each of these steps. So you can imagine when you move up the chain to that final model, there's no way you can get a perfect model. And the good thing is that in modeling doesn't have to be perfect. It just has to be good enough, since we're really just interested in the outputs a lot of the time. So I want you all to just take a second to think about this, like what exactly is a model? If anyone wants to answer, feel free, but think to yourself, what in your life or in the classes that you've taken has like informed your knowledge of like what a model really is.
You're asking a question?
Yeah, I mean, everyone can just think about it, but if anyone has an answer that they would like to give, feel free to. Okay, so just moving on, a model, and specifically a statistical model, is really just a simplified mathematical way to approximate data or reality. And I'm sure the model that you're all familiar with, the one that everyone knows, is linear regression. This y equals mx plus b, so the equation for a line. And this model definitely has its place, but it's not suited really for the type of processes that we're talking about in modeling infectious disease dynamics generally. Other model types like compartmental models, agent-based modeling, time series, survival analysis, these more complex models generally still build on the simple premise. We want a mathematical formula of some sort to approximate reality. So again, it's very hard to simplify human behavior, let alone human behavior for 8 billion people. And again, that's why different models are built for different purposes. So linear regression might be great for looking at the relationship between a person's height and weight, between like one dependent and one or more independent variables. But it just doesn't have the capability to capture something like infectious disease transmission on its own. And that's where something like the compartmental model can come in. So the compartmental model is a simplified mathematical way to look at disease transmission and progression in an epidemic or pandemic. And this final result will yield, this theoretical number or a proportion of people infected. And so obviously, looking at some of the models or hearing about some of the models you might have seen on the news, this is something that might be somewhat familiar. So obviously the jump from linear regression to a compartmental model is very huge. But I do want to reiterate kind of the opposite point that more complexity is not always better. So depending on your time and resources, you may not have the time to make the most perfect model. And even if you are able to use those, if you spend a year trying to make a perfect model, but then at the end of that year, that model is no longer valid or the pandemic has already passed, then what was your point, right? So there is that degree of looking at your time, your resources, and also usability. You want these models to be used. That's the goal of a lot of these models. So kind of moving on to the star of our show, this compartmental model. I'm sure you've all seen, I hope you've all seen some version of this. I know earlier in the pandemic, we had this conversation around flattening the curve. And when we look at this graph, the curve we're talking about is like this red dotted curve. This curve of infecteds over time. The compartmental model, at its most simplistic form, is a way to divide a healthy population or a disease-free population into 3 or more distinct components. So in this one, which is one of the most simple ones, is the SIR model, which involves susceptibles, infecteds, and recoverers. So people in the population or animals in the population will move between these 3 categories as they become exposed and recover from disease. So we are assuming in this very simple model that everyone has an equal infection probability, that the population is closed, so no one is being born, no one is coming in and leaving. There's like even mixing, and that you have a large enough population. And obviously, when we look at those assumptions and try to apply to the real world, a lot of that does break down. So my infection, staying at home, like social distancing, is not the same as someone who is working as an essential worker in a hospital. Obviously, people are still moving between state to state, country to country. And, different people are mixing at different degrees, depending on where they are and their jobs, their behaviors. So even though we do these simulations, there are ways to make compartmental models more applicable to the real world and ways to incorporate some more realism into them. This is going to be a slide that might be, again, mathematically a little bit over the top. So don't feel like you have to understand everything. But in terms of how this model functions by relying on systems of differential equations with our population parameters and certain rates. So you can see in these equations here, what we're looking at are the equations that dictate how people move from one compartment to the next. So depending on, how quickly people are being infected and how quickly people are recovering, that will change the shape of the graph and the timing of the overall pandemic. So again, you can add compartments and rates for more complexity. So you can include values to account for births, deaths, migration. You can add more compartments for vaccination. And really, compartmental models can be very versatile and adaptable. And I think that's why they are like a great tool for epidemiologists to use. At the end of the day, though, they really are tools. And we can use them to make recommendations and to obtain values, but they're not the end. They're a tool for us to reach an end or a goal. Going quickly back to these rates, though, I think that is an important point to touch upon. As you can see here, we have this rate of infection and rate of recovery, and oftentimes we will have to estimate them or we'll have to simulate them, especially for a disease that is uncommon or not so well known, like COVID. We may not have these values, and these will only come out as the pandemic progresses and as we obtain more information. So going off of those rates, though, I do want to bring up this quick point about determinism and stochasticity. Again, this is one of those slides where you don't have to comprehend everything, but I would like to introduce this concept since it does play a role in a lot of the models we currently see. So the biggest difference between deterministic and stochastic models and processes is that deterministic ones are not really trying to account for randomness. They use a known experimental value, or they're setting a known value. So we're saying alpha equals 2.5, or beta equals 0.3. Every time I run that model, I will obtain the same result. I have a static estimate. It's quick, it's easy, but if we're trying to make large-scale recommendations, it probably isn't the best way to go about things. And that's where this idea of stochasticity comes into play. So stochastic models and processes are trying to account for randomness. So instead of saying that alpha is equal to a specific number, we're saying that, we know that alpha is around 2.5, but it could have a range of 1 to 4. And the majority of the time, it will be around 2.5. But there are some occasions where it is super low or super high. And then when that happens, we want to use simulations to get a sense of an average result over 5,000, 20,000, 100,000 trials. And then when we do that and obtain that more average result, we get to see these general trends. So this is a model I made last summer, and a kind of a good example of this stochastic process. So this is a modified SIR model, but as you can see, over the 200 simulations I did, the bulk of the points, the bulk of the lines are for this purple section here. So the recovereds generally follow this trend. There are occasions, when if you look at this one specifically, we have a small purple line. Once in a while, we have a simulated event or a scenario where we have a higher or a lower than expected result. And it's good to know that this could happen, but if we were looking at the realm of reason and the values that are most likely, we would want to look at these. Okay. So now that we've had a little overview of compartmental models, I do want to just point out some of the top ones or some of the reoccurring ones that I've seen and that you may have seen. So these include the Institute for Health Metrics and Evaluation model, which I'm sure everyone has heard about from the White House, as it is one of the models that they commonly point to for recommendations and expected cases and deaths. Yo-Young Gu, who is an independent scientist who created a machine learning-based SEIR model. The Columbia University Shaman Group has their own SEIR, SEIRS model. UCLA has a SUEIR, and Johns Hopkins has another SEIR model. And obviously, these are more complex than the models I've shown to you today, but they still rely on those like underlying concepts surrounding compartmental modeling. So obviously, among all of these, you might find yourself asking, like, which model should I look to? Like, which model should I trust? Which results are the most trustworthy? Which ones should we be using? And the problem is, it's a very difficult question. You might go to a website like this and think, okay, if we're comparing model accuracy, the ones in green are better, the ones in red are worse. But for the general person, this is incredibly overwhelming and perhaps like hard to comprehend. And we don't really need to go into the specifics of this. The question really becomes what you want to prioritize. Every model probably has its place. And we're not necessarily trying to say one model is the best or the most perfect all the time. Sometimes we do have to think about prioritization. So that will involve looking at whether we want to prioritize knowing the number of expected deaths or maybe the number of expected cases. We might want to care more about short-term versus long-term accuracy. If you're a government, maybe you want something that will tell you projected cases in a year, whereas if you're a local health department, maybe you just want to know what's going to happen in the next month. You also might want to think about, more or less complexity. As you get more complex, you are making more assumptions, you are having to spend more time making and calibrating that model. Or, you might want to look at something, more general or specific. Again, maybe if you're a government, you want something that applies to the entire country of the United States. And if you're a local health jurisdiction, maybe you want a model that is specific for Montana or specific to California. And another point that you might want to prioritize is, overshooting or undershooting. If you want a overly optimistic model that undershoots the potential cases, that might be okay. But if you're undershooting, that means you might not be able to save all the people that do get sick if those cases exceed the ones that you expected. If you're overshooting, you might have enough resources and preparation to care for all your patients, but you might be wasting money for supplies that may never be used. And so those questions are things that we all have to think about, but they're also things I can't answer for each of you. So this is like a shorter lecture, but I hope that you can all still appreciate these takeaways, mainly that you can understand the goals of models when one is presented to you, that we're accepting that models are limited and that there's only so much they can do and tell us, that there are trade-offs when we are trying to choose between different models. And then lastly, this idea of not being tied to a single source or model. And this is definitely something I think is not limited just to modeling, but also in the news sources that you read, and I think will allow you all to become more critical thinkers, I hope. If any of this really sounds interesting, I hope you will all consider these like potential careers. So again, epidemiologists generally use a certain degree of mathematical modeling in their work. Data scientists also use models probably on a day-to-day basis, and also bioinformaticians. I will share these slides with Duncan and Dave afterwards, but here are some just like preliminary resources on modeling and COVID, as well as my contact information. I also linked to the Plowright Disease Ecology Lab, since they do have a great COVID-19 blog as well that's more specific for Montana. feel free to contact me. Again, you find my personal research interesting, or if anything in the lecture really appealed to you. Okay. And then I think we're ready for questions if anyone has them.
We seem to be missing our fishing pole,
Okay.
but we're still fishing for questions. If anybody has a question, raise your hand.
So how do we balance between communicating our models with the public, but also communicating the level of uncertainty in those models?
I think that when we communicate that, we should always emphasize that there is going to be a degree of uncertainty. No, again, like no matter how perfect you make the model, there's always going to be a certain degree of uncertainty, like both in like the data, but also in our predictions for the future, right? Right now, like we have very there's more uncertainty about the future like in a month compared to uncertainty about the future today. And I think again, like the more we can emphasize that uncertainty is inherent and greater the further in time you're trying to project and forecast, I think the more more trust we can try to imbue in both like the public and like the scientific community.
Oh, so I have a question.
Okay.
Actually, back a few years back, Singapore got hit with the SARS problem. It was a coronavirus, and the Singapore government was really hurt by it, their airline, their travel, everything. And they didn't want it to happen again. So they chose 4 people in the world to all meet together in a place and discuss what Singapore should do in the future. And one of these people was a Finnish lady from Finland, and she kept track of all communications on the internet. And she looked for specific words. And she suggested if ibuprofen suddenly starts getting a lot of sales in a city or a town with chickens, that was a very unusual thing. And her objective was to very, very early detect an epidemic, because that's when you stop them. Then they asked me what to do, and I'm a different kind of person. And I suggested there are 2,000 biotech people in Singapore, develop 10 SWAT teams, all individual and separate, and be ready for the next epidemic very early as to what to do. And the idea was monitor all airplane flights with temperature sensors of people and so on, and see if you can shut down the epidemic. This sort of thing could work well in Singapore, which is a pretty tight government. It couldn't possibly work in the United States, so I don't know what's going to happen there. But how many of you are computer modelers, or at least computer science people? The interesting thing about that is maybe you should develop your own personal model for how you should protect yourself, and not leave it to anybody else to tell you what to do. That's another thing. So your comments on those comments?
I guess in terms of disease preparedness, it's a hard one. I do think that more and more we are realizing that like spillover and that emerging infectious diseases is a huge area of concern. And I think David Quammen probably has reiterated this, but these pandemic events are going to be more frequent. There's just more and more viruses and diseases emerging and reemerging every single year. And with how interconnected we all are, there's just no way that we can avoid them. And I agree, just being preemptive as possible is going to help. There's a specific program here at UC Davis, along with some other universities in the US, called PREDICT that ended early this year, but is being revived. And the goal is to go out to these like remote places in the world where there's high degrees of biodiversity, and look for viruses in the environment. And I think that's definitely an important component of it. And then I guess on the domestic side is just remaining vigilant, and thinking that it's okay that we're not going back to the old normal, because it wasn't necessarily great or sustainable for everyone in the first place. And I do hope that this pandemic will cause us to be more vigilant, both scientifically, but also in terms of conserving the environment and keeping like those like wild places wild, so there is less chance of spillover and crossover between humans and animal like viruses and pathogens. Dave, what was the, sorry, could you reiterate the second point?
Well, it has to do, are you hear me?
Yeah.
It has to do with a personal model anyway. Maybe you should all be developing your own personal models. They may involve the fact that you have grandparents or something like that. They may involve the cost of obeying your model and all these sorts of things. I'm thinking a personal model might be an interesting idea. Even for our final exam question here is, how does one develop interesting personal models? I don't know.
Yeah, I guess in terms of developing personal models, I will say that most of these models I've talked about are publicly available. So if you go to the website for Johns Hopkins, they'll have the code, or they'll have a link to their code. So if you want to know, how their model functions, if you want to know how to build your own, you can, take pieces of their code and play around with it yourself. If you want to adapt something that's more specific to Montana or to yourself. In terms of very personal models, I know that at least in Germany and also in Virginia, they've like developed apps where you can report whether you've tested positive for COVID, and that will let the people around you know who also have the app, to like avoid that area, or to be vigilant about wearing their masks and using hand sanitizer and washing their hands in that area. And I think these, altruistic models are definitely an important part, because it is a social disease. If we weren't social animals, this disease wouldn't be as big of an issue. But because we need to see people and need to work and interact, that is where it does become part of the problem, because there's no way we're going to eradicate all contact and communication between people, right? Does anyone else have any other questions or comments they might have?
Okay.
That's just what I have to say.
I'm sorry. I'll ask the question again.
Okay.
Is there a genetic component for introverts or extroverts? And the fact that we all evolved from a very small population, but we're now in a very large population. Do you know of any genetic components for introvert or extrovert?
I'm not quite sure. I would assume there probably are genetic components, but it's not quite my area of focus, so I would have to get back to you on that. But I guess like that does pose a interesting question about how much like introversion, extroversion does play into disease transmission dynamics.
Well, one thing we know is that with at least COVID, you can hear me? With
Yes.
COVID, males tend to get it twice as often as females. Is that true?
I believe so. I guess there's a lot of social factors that could affect that. Maybe in certain countries, more men are employed than women. Perhaps men are in fields that involve more social interaction than women. Maybe men simply just have worse outcomes, and they have symptoms that are worse. So that maybe men and women are being affected at the same rate, but because more women are asymptomatic, it would appear that more men are being infected.
The same question could be asked of other creatures than humans, such as bats. Do males bats get it more than female bats? And so on.
Mhm.
These are all interesting biological questions, in my mind, okay?
Mhm.
I guess Linus Pauling said, if you want a good idea, have lots of ideas. Always be as open as you can on ideas. Now, I once had a student who was a vegan from birth. And when the whole microbiome thing came true, and everybody was suddenly saying microbiomes are interesting, this student streaked him or herself for what bacteria were in her gut or his gut. And what they found is that the vegan had a whole bunch of E. coli that excreted tyrosine, which is converted to dopamine. And so the rest of us in the lab immediately streaked ourselves, and we found that our bacteria were excreting lysine, not tyrosine. And actually, this was a very interesting.
Hang on. Your mic died.
Okay, we're having a little sound problem. I'm sorry. But actually, Sophie was very aware of that experiment. And I think the point is there's a ton of experiments that you can do, but it's best to be like a surfer in whatever you're working on, be it toxoplasmosis, which Sophie works on, or whatever. When something new hits, like COVID, you have to jump on the horse and try to ride it a little bit and use your knowledge in some way, like in the Singapore case with myself. So I think keeping open, this idea that when you get a doctorate, you've reached a goal. Actually, the goal should be self-learning for the rest of your life and constantly taking in new information. Sophie, could you tell me what books you've read recently?
I haven't read that many scientific books recently because I've been learning another language, but let's see. Sorry. What have I read? Yeah, I mean, just to reiterate Dave's point, I don't think that getting a doctorate or like going to grad school in general is the only way that you should motivate yourself to keep learning. Like obviously, not every one of you will want to get a PhD or continue down in getting like a degree in biology or whatever it is. But I think there's still like a lot of room to learn from other disciplines as well as the one you're interested in, just for your own knowledge and also just for your own like self-improvement and to expand your worldview. Because I do think like that is an important component of like learning, because the more information you're exposed to, the broader set of experiences and knowledge you have, I think the more well-rounded and more creative you can be, because you have a larger base off of.
I agree. I get a magazine called New Scientist. It's published in the United Kingdom, and it's a little bit expensive, but it has maybe 40 articles a week on different science type advances. And keeping broad in your view of science gives you many, many ways to solve a problem. And I think that's very important. If you look at Sophie, she's in a very specialized field right now. And it's very important that we avoid being in the silo like that in one field. Now she's in 3 or 4 fields, but still the same applies to all of us. I think we should constantly be looking at different ways to solve a problem. I'm trying to change the name of this university to the University of Problem Solving rather than just State University. What do you think of that, Sophie?
I wish you all the luck, and hopefully it will happen at some point.
Well, I doubt if we'll change the name. We spend too much on marketing and too much on things like that. But there are huge ways to solve problems now with computers, with artificial intelligence. The problems are constantly coming at us, like COVID, like global warming, like GMOs. And we have to be ready for these things. I wish you guys luck. Hang with the course, get what you can out of it, and develop your own idea train. As Linus Pauling said, you want a good idea, have lots of them. If you have them early on in this course, you'll be able to write a really easy essay, which is what your grade will be based on. Thank you very much, and thank you, Sophie.
Yep. Thank you.